All right. Ask questions, home audience. Hope you're all set, and we're just going to dive into it. We're going to look at final exam from spring 2014. I think that will be a good exam to look at. It's posted on the course website. So final exam, spring 2014. Now I'm going to put up the first figure if you want to copy it down first. Then we'll read the problem together. But you can probably tell this is going to be some kind of an amplifier problem. Okay. Again, a high priority problem. This is where, Darcy, we need some background music. We'll have to work on that for next year. Some incidental music, you know, just to kind of smooth into the next transition. Now, my colleagues, as you're writing this down, I'm hoping that this problem is talking to you. Okay, it should be talking to you and should be telling you how to solve it. See, I see right here. I know what this end is saying. REQ, REQ, right? And if I combine those into one resistor, if I'm asked for V out, this is a voltage source. I think I can use voltage division. So you should be getting to the point where you can see that. And I look over here, I have to get V in. I'm thinking another REQ. And voltage division, which should be REQ over R1 plus REQ times VS should equal V in. So I don't know what the problem is asking yet, but I can see that if I'm asked to get V out, I think it's 2 REQs and 2 voltage divisions. You know? So already you have a game plan. So with this now copied, let's now look at the first problem. Now before I do that, my colleagues, if you look at the last page of this handout, there is the formula sheet. So if you have any questions as to what's on the formula sheet, just look on the website. Okay, the formula sheet is effectively exam 3 and I think exam 2, right? Did I? I guess I didn't. Well, I would give you the formula sheet for exam 2 also. I'm sorry if that was an oversight on my part here. Okay, so let's now look at these are the solutions. Well, okay, we can look at them. Okay, so it says here, refer to the attachment, figure 1, and it says determine an expression for V out over Vs. My colleagues, I think it's just as what we were discussing. Okay. If you look at the figure in front of you, home audience, help me out. My colleagues, please stop me if I'm not clear. We have an REQ on the right-hand side, which is R5 and R6 in parallel, which is product over the sum. And then how did I get V out? I'll show you the formula, and then I'll just take a quick look back at the figure. V out is given by, now I know you're copying this, I'll come right back to it, but look what we're doing. We're finding an REQ, and once you find an REQ, you can then use voltage division because I have everything in series. Okay, so find an REQ, and then express V out as REQ over REQ plus R4 times this dependent voltage source. That's what you'll see right here. Now, I've met with a number of you to go over your exam 1, and what I've shared with you is while this is the right answer, I think you can easily simplify it. And I call this like a sub-basement, this is like a sub-denominator, okay? Just take what's down here and multiply the entire numerator and denominator by that. And what you'll get is, in the numerator, just R5, R6, and in the denominator, R4 times that term, and then R5, R6, the denominators cancel out. The denominator cancels out, and you're left with this. Now you got, I think, a really nice expression for V out over V in. Now, we're not done yet. We're not done yet. We're asked to get V out over Vs. So if you go back to the circuit drawing, I now have an expression of V out in terms of V in. What I need to do next is to get V in terms of Vs. Again, same thing. Okay, so voltage division after I combine R2 and R3 as an REQ. And that's what I should now have in my solutions. Okay, so if I scroll down, we get pretty much the same approach. We have an REQ using voltage division and then multiplying by the bottommost term. I think you get a very nice expression for V in over Vs. Now, you can write that as V in equals this times Vs and then substitute it in. And I think I might do it a slightly different way coming up. How am I doing so far here? We're all good on the amplifier problem? Home audience, I hope you're okay. All right. No, I don't think we were given a value for A. That's for the dependent source. I think everything was just variables. All right, so what happens next is V out over Vs is V out over V in times V in over Vs. Now, if you see it that way, that's fine. My colleagues, before you write this down, let me just pause. Some people don't see it this way. What you could do is just write this as Vn equals this times Vs. And then take all of this and substitute it into this equation. Sorry, my cursor. Here. See, here you have V out equals something times V in. The second part of the problem had V in equals something times Vs. You could just substitute in here for V in. You get the same answer. Perhaps a slightly more elegant way, but you don't get extra points for being elegant, is V out over Vs is V out over V in times V in over Vs, both of which we now have. And we just put it all together, and that's good enough. Okay. So that's the first part of problem 1. So far, so good? Thomas. Right. If we have a sub-denominator, is that okay? It probably is. But just to give you the heads up, this is how I'm going to write the answer key. And you all know in advance the TA's got 400 exams. So if you know the answer keys like this, if you don't have to have them pause and do a think, you'll probably get a better chance of getting it marked perfectly correct. So if you could simplify it down to this, that would be perfect. Darcy, the audio quality is still good? Fantastic. Thanks, Darcy. All right, so that's the first part. Okay. I don't think I see anyone else copying. Question is, how many questions on the final? Just enough. Not too many, not too few. I have not made up the final as of this recording, so I honestly do not know. This final has 6. But it will be the Goldilocks principle. Just right. Okay. All right. So, my colleagues, we now go to a second problem. But it's the same problem. I should be careful. It's part B of problem 1. It says the input resistance of an amplifier, in this case, is defined as V in over I in. Determine R in. So before you write this down, let's just go back to the circuit. V in over I in. So if you noticed, this is V in, and this is I in. So we're asked to get a relationship of V in over I in, and we call that the input resistance of the amplifier. So you say, fine. What you really want me to get is V in over I in. Now, what I did to make the solutions hopefully understandable is I redrew the left side of the circuit. And again, I'm going to combine these two. Since they're in parallel, V in is the same across R3 and R2. So I now combine it, and as you all should very well know, for two resistors is product over sum. I then say, okay, what I want is this relationship. And what I notice is that V in over I in, excuse me, let me follow what's written here. V in equals I in times R equivalent. If I go up here, see, V in is across those two resistors in parallel. That's REQ. And I in is the current that goes through REQ. So REQ times I in is going to equal V in. We're good? I think I see a question. I think I see a question. I think I do. I have one over here. Yes, sir. Okay, if the current is somewhere else, that's a different problem. We can discuss that some other time. Tonight, let's solve this final. Thomas. Could we also describe I in as Vs over R1? Hopefully not. Okay? Because the I in would be Vs minus V in over R1. All right? So my colleagues, don't make that mistake. Vs over R1, did you say R1 or I in? Right, that would be incorrect. So let me make sure we're all comfortable with that. Thank you, Thomas, for pointing that out. Vs over R1 does not equal I in. Right? You have to get the voltage across the resistor. So that would be Vs minus V in over R1 is I in. How am I doing? Okay, question.
So is that the top equation you have is Rn is equal to V in over In?
I'm sorry, say that again.
The top equation that we have is that Rn is equal to V in over In.
Right, that's given. That's just given. So you don't have to know what that even means. Just say, what I need to get is the V in over I in. That's really what I'm asking you. And I'm telling you that that happens to be what's called the input resistance of the amplifier. I sense you have a follow-up. No, we're... No. Oh, is it? Hold it. Is it? Yes, the way I've defined it. You're right. You're right. Okay? So in this case, I stand corrected. You're absolutely right. So it turns out that Rin is REQ, and that's the answer. You're absolutely right. Perfect. And that's the input resistance of the amplifier. Great. Thomas, we're good? My colleagues, we're all good? All right, so that's part B. I'm looking around to make sure we're okay. All right, looks like we got it. If not, just, yell out. Ah. A load resistor is now placed. Everything in your body should now be going, Thevenin, Thevenin, whoop, 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 Thevenin, Thevenin. Okay, so we now have a load resistor placed between terminals A and B. Determine an expression for maximum power transfer. What should this load resistor be for maximum power transfer? Without even using the word Thevenin in the problem, I'm giving you a Thevenin problem. So what you should know is that I need to get V open circuit divided by I short circuit. So you got to solve this problem 2 times. So you need V open circuit and I short circuit. Now, R Thevenin would then be the ratio of VOC over I short circuit. So I say, all right, now V open circuit is V out. Let me just pause for a moment. See, here are points A and B given in the figure. All right? V open circuit is here. We already determined V out, which is V open circuit, in part A. So we already have half the problem done. So V out is V open circuit. We're going to get that answer directly from part A. Now, we then have to solve the circuit a second time. We have to put a short circuit, which means a 0 ohm path between A and B. So we put a short circuit from here to here. All right? What is now the current in R5 and the current in R6 if I have a short circuit here? Exactly. Good man. 0. That's because I have a 0 ohm path in parallel with these 2 resistors. So what happens is I got a short circuit here, and as I'm hoping you will see, but we have it written down, the current is just going to be V equals IR, I is V over R. Okay? And then that's going to give you the short circuit. So let's go back and look at the solutions. Okay? So we have V out is given here. I short circuit. Now please let me know if you have any questions. I short circuit is V over R. Okay? And the only resistance now, because the other 2 resistors are what we call shorted out, the only resistance on the right-hand side of the circuit is R4. And the voltage source is that dependent diamond AV in. So I short circuit is then AV in divided by R4. So we say, okay, I now have R Thevenin by just taking V out, or V open circuit, and divide it by I short circuit. Now look what happens. I'm thinking of Thomas's point from earlier. Isn't this very nice? The AV in cancels out. And the R4, since it's 1 over R4 in the denominator, that just comes up here. So this is now a very nice way to write the load resistance for maximum power transfer, which is important to know. Because if this is an amplifier, I've designed it to power something. And I usually think of it as an audio speaker. I want maximum power to that audio speaker. How are we doing? Thanks for the feedback. Matt, we're thinking of you tonight. All right. Okay, that's the amplifier problem. We now on to problem 2. I'll show you the figure coming up next. How do we do so far? Too easy, I can tell. See, I know it's too easy because you're smiling. See? All right, that's good. You got it. That's what's important. All right. Okay, let's see if we can liven this party up. All right. This looks like a first-order differential equation kind of problem. You know, it might be the same circuit. I have to tell you, as you're writing this, I do not look at previous exams. But I've been teaching this now since the fall of 2010. And every now and then, I look back and say, oh, my goodness, it's the same circuit. And it's not because I didn't sit down with a blank piece of paper. It's that I think my mind only has a finite number of combinations to work at here. So I sincerely hope I don't disappoint you. I want to give you new and freshness. So, but yes, this is probably similar to what we've already looked at. And I'm sorry for that. I do try and change it up. I don't cut and paste. It's just there's only so many ways I know how to ask this. By the way, if next semester, if you have any suggestions on how I should ask E245 problems, let me know. All right, we'll make it really hard for the next group of colleagues taking it. All right. All right, I think the way this is, I'm going to ask you something about V sub C of t. All right? Now, if I'm going to ask you about V sub C of t, what method, if I'm asking you for voltage, what method are you thinking of? Nodal. Right. So where am I? I'm in the node. I'm in the node. All right. So I see the switches at t equals 0 changing. So my colleagues, it's very important you take your time. A simple misreading of the problem, and you could solve it using all correct principles, but have your switches mixed up. So take your time. There's no rush. Saturday, you got 4 hours in the afternoon. Come on, it's cold outside. Stay in here 4 hours and just work it on. So let's now go look at the problem. All right, so part A is write the first order differential equation for V sub C of t. Now, home audience, studio audience, it's very important that you go from the complete circuit drawing we just looked at to this. If you get this step wrong, everything else is wrong. So you should look at what you drew and say, okay, what am I looking at? T greater than 0. If I remember, switch 1 is closed and switch 2 is open. Okay. So you should convince yourself the circuit reduces to this. Is everyone with me? All right. Now, God bless. The next thing you should know is that this entire node, now you have to know this. I'm not putting the dotted line on the exam. You have to know that this entire node is now V sub C of t, right? V sub C of t is across the capacitor. Slide your fingers. I'm not hitting anything but just wire. So that entire node is V sub C of t. Now, doing nodal, you should feel very comfortable with this. I'm hoping you're feeling great, okay? So you should be able to write this as V sub C of t minus Vs over R1 plus V sub C of t minus 0 over R2, the same for R3. And for perhaps the last time of the semester, we know how to chant I equals C dV dt. Now, we need to put that into standard form. All right. Putting that into standard form, we gather all the R's and we, 1 over R's. And I say, okay, I got this. Finding a common denominator here. And then you get it all in standard form. How are we doing? We're good? Thank you. Thank you for the feedback. My colleague, we're good? Good, okay. All right, so you should feel very comfortable on doing this. Now, I'm going to ask you on the next page, I think, a couple of questions. Before I get there, Thomas. Yeah, but there's not an R1 everywhere. Oh, I beg your pardon. This and this. Absolutely. You're absolutely right. That's a simplification I should have done. Excellent, Thomas. Excellent. Are we good, my colleagues? All right. Now, what I'm hoping you know, tau. Oh, but by the way, let me back up. This is a standard form because there's a 1 in front of the non-derivative. Okay? Now, tau in standard form is whatever is in front of the derivative. So this is tau. And since this is a constant input system, the right-hand side is the particular or steady state solution. Remember, that's what particular means, steady state. So I look here and say, great, time constant for the system is given here, which is the coefficient in front of the first derivative. Now, my colleagues, I might try to trick you up. Instead of saying the homogeneous or homogeneous solution, I could call it the transient solution. Right? Transient is the same as homogeneous. Now, how do I get the homogeneous solution? Don't let me down. What is it? Someone help me out before we look at the answer. Thomas. Fantastic. That's it. Now, the particular solution, which is the next question, the particular solution is also the steady state. So I could ask you that. Or I could ask you the value of the output as t approaches, value of v sub c of t as t approaches infinity. As t approaches infinity in this problem, we reach the right-hand side of the standard order, first order differential equation in standard form. We reach that right-hand side, and we get here that that is v sub s. And Thomas, you're absolutely right. I guess by the time I got to part D, it dawned on me I could cancel the R1s. All right, good. My colleague, I sense a question that do you have anything? We're good? All right, good. My colleague in left field. Excellent, because e to the minus t over tau goes to 0. This is a very good question you ask. Let me repeat it. The total solution is the homogeneous plus the particular. So as t goes to infinity, e to the minus infinity goes to 0. So it takes out the k also. So the whole thing is gone. And all we're left with is the particular or the steady state solution. Good man. That was a good question. You responded to what I was saying. Thank you. All right, we're good? Okay, now, determine the complete solution. Now, before you write this down, I'm going to give you plenty of time to write this down. Here's the circuit, right? Now, what have we done? We've closed this switch, and we've opened this switch. Now, to determine the complete solution is the homogeneous plus the particular. But I need to know the value of the voltage across the capacitor. Now, here's what's so great. I'm just going to go over here and write this down. Turns out the voltage across a capacitor cannot change instantly. So the voltage across the capacitor at t equals 0 plus equals the voltage of the capacitor at t equals 0 minus. Now, it's going to be very easy, as I'll show you, to determine the voltage across the capacitor at t equals 0 minus. Why? At t equals 0 minus, this switch is still open. This switch is closed. And in the statement of the problem, I say the switch has been closed a long time. What am I telling you? It's closed 5 tau. My colleague, you had your hand up? Perfect. And the capacitor, if you can go 2 for 2, you're doing, right, open, exactly. Excellent. Good man. So what happens is this inductor in steady state is a short circuit, and this capacitor is an open. This now reduces to an all-resistor problem. Chapter 2. And as you'll see, we have an REQ and a current going through an REQ. I got it. Excellent. Thanks for the assist. So now if we go back to here, I wrote down here that L, the inductor, is a short circuit, and the capacitor is an open circuit. So what we have then is a current source with 2 resistors in parallel. So I do an REQ. And it turns out the voltage at t equals 0 plus, which is what I want, is equal to the voltage at t equals 0 minus, which is equal to REQ, times I. So it's pretty okay. It's pretty easy, I think, to figure out the voltage at t equals 0 plus if we look at t equal 0 minus. Okay, so then we say, all right, what do I now have? I have this from the previous page. The capacitor voltage is the homogeneous, as my left fielder was discussing with me. It's the homogeneous plus the particular. That's the total solution for V sub C of t. I now know something else. The voltage across that capacitor, t equals 0 plus, is just what we derived above. And I set that equal to this side, and I also have to let t equal 0. So I get k e to the minus 0, or e to the 0, plus this term here. And what you'll see on the next line is V sub C of t at t equals 0 plus is equal to all of this. We're going to solve for k. So k is this term minus the other term. That then gives us k. And now at this point, all I have to do is plug the k in, and Grace, we're done. We're done. We plug in the value of k. And there we have it. So you've solved I think a somewhat challenging. I don't mean to make them similar all the time. I'm going to try and work a way to make them different, but this is what you get. How do we do? All right, now I ask you a question I don't think I've asked you on exam 1 or 2, or exam 2. So I say, let's see if we can, first of all, simplify the equation we just wrote. My colleagues, if I go back for a second here, this looks a little unwieldy. All right? So I'm going to ask and tell you to substitute something for the first term, what's in parentheses. and something for the second term to make things a little easier. So where do we leave off? Solving the entire equation for V sub C of t. Now I say, wait a minute, that looks a little messy. So I say on the second line, define the constant in the homogeneous solution to be k. And define the particular solution, which is also a constant, to be k1. So my colleagues, we can write the equation that I think you might have just written down as ke to the minus t over tau plus k1. Simplify it just a little bit. Okay? So now I say, determine an expression for the time it will take the capacitor voltage to reach X% of its final value. So I say, wait a minute. Darcy, I'm going to write this over here. We're going to try blue this time. Okay. So this is time, and this is V out. Now, the dotted line is the constant input. Or excuse me, I should be careful. The dotted line is the eventual output, the final output. So the dotted line is the final output. This is the initial condition. So what happens is it starts to exponentially rise. So we're asking for an expression for the amount of time it will take to reach X% of the final value. For example, 90%. Okay. So I come here and say, all right, how are we going to solve this? So suppose X was 90%. And the final value, by the way, this is what you have to know. This is the key. What's the final value? The particular solution, K1. Okay, excellent. So we want to reach X% of K1. So, just kind of reason it out. Suppose X1 was 90%. So that means I want to reach 90 over 100 times K1. 90%, right? So I want the final value, I want to find out the time it takes to reach X%, or 90%, 95% of the final value. So what I do is I go back to this equation here, ke to the minus t over tau plus k1. I go back there, and I say, I now want to know the time it takes to reach X over 100 times K1. And I set that equal to ke to the minus t over tau plus K1, and I solve for t. This is new, so I'm expecting questions. Home audience, we got the studio audience thinking, my left fielder again, help me out. This is, you ask a very insightful question. Okay? Now, I didn't expect this question to come up, so what I'm about to say is a little bit detailed, but I think it's a fun question. How did you start out your question? Let me stop right there. Great question that starts out assuming K1 over K is bigger than 1. Turns out that's not the case. In fact, it's also something very interesting if it is. You bring up a fantastic point. Here's what happens. I need your help to make sure I answer your question. K1 is the initial condition, right? Right? That's here. K is the particular solution, the final value, here. All right? So K over K, which is bigger, K? So K1 over K is a fraction. Right, so this becomes the log of a number less than 1, which is negative. And I have a negative sign here. Right. Right. Right, we're in trouble, right? We're in trouble. Wait, I thought about this. Wait a minute. I thought about this. I have an answer. I'm drawing a blank, and I don't know why. I've looked at this, and I know I've gotten this answer. Wait a minute. Wait a minute. Time out. Did I get my notation mixed up on the whiteboard over there? K is the initial condition. K1 is the particular solution, right? So K1 is the particular solution. I drew it upside down. This is K. This is K1. Right? You asked a great question. My home audience, I'm sorry. I drew it wrong on the board here. Let me go back and just read this again. I want to make sure there's no doubt. I don't want to have your faith in me shattered. Okay. It says here that the constant for the homogeneous solution is K. Okay. That was determined by the initial condition. And it and that's no problem. That I can handle. I'll be right back with you, sir. That I can handle. It was when I was getting a negative number in the log that I couldn't handle. See, look, do we agree that the way I drew it here, K1 is bigger than K? My left fielder, are we good? My colleague who just asked that question, for now, the way I've drew it is K1 bigger than K. Okay, home audience, I hope we're all right. So what then happens, if K1 is bigger than K, what we have is a number less than 1, but it's positive. We get a natural log of that. My colleague, a natural log of a number less than 1 is negative, but I have a negative sign here. So the t becomes positive. No, we're not having a negative log. In the example I've drawn over here, K1 is the final value. If we start at an initial condition below that, we wind up with a number less than 1, but not negative. Am I? Ah. K is smaller than K1. I got your point. I'm sorry. Home audience is saying, come on, move on, move on. And I'm thinking, I thought about this. K1 is negative. Thank you. K1 is negative. K or K1? K? Here, my colleagues. That's K. K is right here. My colleagues, my colleague, help me out, because you asked a great question, and my colleague here gave me the assist. No, you gentleman right there, you're the man. It's this quantity minus this is K. This is the final value. This is the initial value. When the initial value is lower than the final value, K is negative. So what's happening is two things are in play. K is negative, which makes it now be a positive number. And the number is less than 1, total quantity inside the square brackets, which makes the natural log of this negative. But we have the negative sign here, which makes t positive. How did I do? Thank you, thank you, thank you. Now, something interesting. Suppose we didn't have this curve, but we had an initial condition. Now, this gets to your point. Suppose the initial condition is higher, right? What happens is it's an exponential decay. Does it ever reach 90% of its value? No. That's why we get then an undefined solution. That's what I remember looking at. This is very interesting, isn't it? I'm sorry I didn't know this right off the top of my head, but I'm surrounded by really smart colleagues, and we got it. Thank you. Thank you, thank you, thank you, thank you, thank you, thank you, thank you. Are we good? Good. All right. All right. So now that gets us this expression here. We're on to problem 3. Now, I want to say something important, and I wish I had a way to shake our home audience in case you're fast forwarding. Don't fast forward. Stop. There's 6 problems in this exam. There's one topic in particular that for this year I didn't ask. But I can ask you. I didn't, in this exam, have a second order problem. I would like everyone to write down a second order problem is possible and indeed likely. So how do you prepare for a second order problem? You look at exam 2, wasn't it? Exam 2. There are 2 versions. Look at both and you'll be fine. So home audience, I hope you're not fast forwarding. Stop, 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 all right? There's most likely going to be a second order problem on the final exam, even though we're not reviewing one tonight. So look at exam 2, both versions. So I don't want to see you Saturday afternoon at 5:15 and your head is hanging down saying, I didn't know there was going to be a second order system on the exam. No, I'm telling you, there's a good chance it's coming. All right. Now, we're up to problem 3. By the way, I'm loving this review. You're making me really think. I love it. Thank you. Thank you. And the assist right here. Right here. All right. So, problem 3. Oh, come on. This is easy, isn't it? My colleagues, what do you think of these problems? Is this problem too easy for the final? It's challenging, right? It's very difficult. Yes, I should definitely keep something like this. All right. So this is nodal, excuse me, in sinusoidal steady state. Nodal in sinusoidal steady state. So I give you all of this, and I am going to ask you to determine V1. My colleagues, I have to believe this is fresh in your mind, and there's probably little I can say that you haven't already learned on this. Let me see if I can just write the equation by just stepping through it, and then we'll look at the solutions. This is V1 minus 10 at an angle of 45 over 10. This is V1 minus 0 over 10 minus J10. This is V1 minus 0 over 10 plus J10. And then because the current is going in, it's minus 5 at an angle of 45 degrees. Sir? Yeah. Yeah, help me out. You're asking a great question. I hope I didn't say it wrong. Let me repeat that again. My colleagues, we have an excellent contribution. I would write this, forgive me if I said it wrong, as, see, when I'm in the node, I assume the current flows out. So I would write it as V1 minus 10 at an angle of minus 45 degrees. Did I forget to say the minus? No. Okay, so it's V1 minus 10 at an angle of minus 45 degrees over 10. Are we good, sir? My colleague, I know what you're thinking, and our colleague is questioning, and rightly so, the direction. Two things come to mind. If it was a DC battery, we always did this in chapter 2. V1 minus Vs over R1. Now, I do remember, and I think this is what you're discussing, when we got to real and reactive power, to help sometimes the problem to make it a little simpler, to save a step, I showed the current going this way. In that case, you can do what, you can then assume the current flows that way, because we had to get I and V of the source to get the real and reactive power. Here, I'm just doing traditional nodal. Did I do okay? Good. All right. So my colleagues, let's see how I did. And so we have V1 minus 10 at an angle of minus 45 degrees over 10 plus the two middle terms I've discussed. And then since the current is going in, it's minus 5 at an angle of 45 degrees. Now, the rest, if you don't mind, I'll leave to you. Okay, I have it done step by step, so you can look at this on your own. I do it step by step, and I get an answer. Again, the key things to note is if I want to divide or multiply, put things into polar form, which is the vector and the angle. If I want to add or subtract, put things into what I call Cartesian, which is real plus or minus the imaginary part. I think, given that this was just on exam 3, and I think the best way to learn this is to just do it, and all the solutions are here, I think you're good on problem 3. Any questions? Anything I can help with? All right. Darcy, we're moving along here. All right. Here we go. We now have yes, how can I help? Yes. The only part of problem 3, Thomas, I hope I didn't miss anything. Let me go back and check. The only part for problem 3 was determining V1. All right, now problem 4. I give you the nodal voltage. Now, Thomas, I'm wondering if you're reading my mind here. Right after problem 3, there's a problem where I ask you to find real and imaginary power. And I was thinking if someone made an accident and made a small error and calculated the incorrect answer for the node voltage, that would mess up all their power calculations, even though they might know how to do it. So I gave a second problem, similar structure to what we just looked at. And I gave you the nodal voltage. So even if you made a mistake in the previous problem, it won't carry over. So problem 4 says, okay, here it is. I'm not asking you, kappa seg, to figure out the voltage 1. I'm giving it to you. Okay? But now what I'm going to ask is real and reactive power. All right, so with this in mind, let's see if we can calculate what we're asked to figure out. So I go back to figure 4. Determine the reactive power delivered to the capacitor. Now, there's at least 2 ways of doing it. The reactive power to the capacitor. So I'm hoping you remember from chapter 2, V equals I squared R. Oh, excuse me, power. It's getting late. Power is I squared R, and power is V squared over R. Well, a similar formula applies for capacitances and inductances. So I say to myself, okay, I could use either the voltage across the capacitor, or I could do the current through the capacitor. That's what I need to calculate the reactive power to and from the capacitor. So you could do voltage division, or I could figure out the current through this capacitor. So I'm hoping you see that you have a choice. Now, I forget if I solved it both ways or not. So what I did was I determined in the first approach the current through the capacitor. So Ohm's law now applied to impedances. V equals IZ, not V equals IR. We now have an impedance. Remember, an impedance is a resistance plus a reactance. So I now get that the current is the voltage divided by the reactance. I plug all this in, I get the current. I then say the Q, reactive power, to and from the capacitor. Think of I squared R, except it's IRMS squared times the reactance. Now, for the reactance, I take the sign, not the J. Remember how to get IRMS and VRMS? Divide by 1 over the square root of 2, or divide by the square root of 2. Divide by the square root of 2. And I get minus 0.51 VARs or watts. Now, some of you may see it the other way, and I gather I solved this here. You could determine the voltage across the capacitor. And the voltage across the capacitor, to just show you that, that's minus J25 divided by 25 minus J25. times V1, which is 7.14 at an angle of 45 degrees. So you could use voltage division if you wished. So, my colleagues, I now have voltage division. I plug all this in, and by golly, I get the same answer. Which means I've either done it wrong twice, which is entirely possible, or maybe, just maybe, we might know what we're doing. Same answer both ways. We're good? All right, continuing on. Determine the reactive power delivered to the inductor. I think it's pretty much the same problem. I could figure out the current, or I could do voltage division. So either way, I'm going to get the same answer. Okay. So I'm wondering if I did it both ways again. So I get I sub L is V1 over Z. I get the current, and I basically use I squared R. Thomas, help me out. Yes, if I remember, this exam had the power equations. You can check me out, Thomas. It's the last page of this, of not the exam, but the figures. Good. And the other thing is, I noticed tonight, which kind of threw me a little bit, I didn't have the exam 2 formula sheet, which was for second order. So you'll have that also, because I'm pretty sure you'll be getting a second order problem. Okay. So you should have, if I have it right, 2 formula sheets, the exam 2 formula sheet and the exam 3 formula sheet. Thank you. So now I could also do this by voltage division. All right. Lastly, determine the total real power delivered by the source. Before we get there, my colleague, this is what I was thinking of your comment earlier. But before I get there, my colleague, my left fielder. Right. My colleagues, our distinguished left fielder points out that it's the same power, just the opposite sign. Yes, but be careful. I must have been struck with exceptionally good Christmas cheer when I was making up this exam. The middle 2 branches are essentially identical. If I changed anything, the observation wouldn't be true. So as long as you know that. Okay. Thank you. The next one is so the comment from our left fielder was one answer is plus 0.51, the other answer is minus 0.51, and that's because the two branches are essentially symmetrical. They both have a 25 ohm resistor, and the reactance is 25 ohms, but one is minus J, the other is plus J. All right, the next one is determine the current through the source, because I want to get the total real power delivered by the source. And so what I did was I calculated I. Okay. And by calculating I get, remember, if I want to add or subtract polar vectors, I have to really convert them to Cartesian, which I did here. And we then get an expression for I. And after I get I, we then use the formula, and Thomas, this will be given to you, VRMS, IRMS, cosine of theta. What's theta? The angle of the voltage minus the angle of the current. They're both 45 degrees, so I get a value here of 1.4 watts. I suspect I might have asked you the reactive power. I don't know if I did that or not. We'll see in a moment. How are we doing so far on this? We're going good? Okay. Let me know, my colleagues, if you have any questions. We're up to figure 5. Absolutely. All right. Thomas, we're good? Great. Okay, figure 5. Or problem 5, pardon me. Now, my colleagues, remember, you should know both low pass and high pass, okay? So it's like a pitcher in baseball. I'd like you to be both a lefty and a righty, so it will make you very valuable. Wasn't there a pitcher from Japan who signed up for the Dodgers? And I think he got injured last season, who was both, no? Might have been, right? I forget, I don't know. All right, so my colleagues, you got the figure. I think I'm going to ask you the transfer function. And I think I'm going to give you a V in, and I want a V out. And I think I'm going to ask you to draw a Bode plot. That's what I think. So let's see what we got here. So it says here, determine an expression for the transfer function of the filter. Now, before you start copying it down, and I want you to, I just want you to read this first. Turns out that you can get this into standard form. It's actually quite nice. But there's a couple of steps that I don't want you to get caught up on. It's algebra. So I say, look, you do not have to get this transfer function into standard form. You don't. Okay? Just get me the transfer function. And here's what I would like. In the numerator, j times something divided by something plus j something. Now, you might remember, and if not, you can look it on the formula sheet. This is a high-pass filter. And you might remember that this term here should be 1. Now, it's fun to do that, but I don't think it's fun on a final to do the algebra to get this to equal 1. So I say, forget it, keep it as some kind of term. Okay? So what I'm asking for is j times something divided by something plus j times something. What I'm going to give you on the final. By the way, you make me disappointed. You made such wonderful comments tonight. I was hoping you might have that buried in your mind, but that's good. That's a fair comment. Here, how about that? Low pass, high pass. Good? That's what you're going to get on the final. Does that answer your concern? Did I get it? Right, but notice the low pass doesn't have a j in the numerator. I told you it was j times something, right? Has to be high pass. So if on the final you give us what form it has to be in the question, we'll know if it's a high pass or low pass. I'm saying, do you think you'll give us that same thing on our final or not? I don't know. I'm going to give you a circuit and ask you for the transfer function. And if the transfer function is crazy, I'll give you a hint like I did here. But I might just do it like I did on exam 3. not tell you if it's low pass or high pass, but you knew it was low pass because high pass wasn't on the exam, you should be able to easily figure that out. Sounds good? All right, thanks. So, my colleagues, here is question 5. And the approach I would use is voltage division. Now, we started out tonight with REQ in problem 1, the amplifier problem. So here we have a ZEQ. If you look at the drawing of the filter, we have an R2, I think, right? R2 in parallel with L. Okay? So what we do is we take the product over the sum. R times J2 pi FL, that's the ohmic value of the inductor, divided by the sum. And I say, all right, can I do anything to make this a little easier? What I did first, I just put the R2 at the end here, okay? Desperately searching to do something. And I say, okay, what I can now do is voltage division. V out equals, remember how we said R2 over R1 or REQ plus REQ over R1 plus REQ? Same thing here. It's ZEQ over R1 plus ZEQ times Vn. Now, you know myself and sub-denominators. What am I going to do here? I'm going to multiply, right? I think. Right. So, gives me this. Okay. Now, I'm almost there. Am I doing okay so far, sir? I'm almost there. Continue on the next page. What I get is this. And we're just about there. How am I doing? All right. Absolutely. Can I scroll up? Absolutely. Does it make sense? Let me know if it doesn't. So from the previous page, I get this, and I rewrite it as this. Now, it turns out there's only a couple of more steps to put it in a really nice form, but it's one of those things you either see it or you don't, and I didn't want to give you that on the final. So this is good enough for me. So this gives you the output over the input for this circuit. Are we good? All right. So that's part A. Now, because there's the J in the numerator, I'm thinking this is a high-pass filter. So I then give you numbers. For R1 and R2 is 10 ohms and L is 1 millihenry, and you have a V in. Tell me V out. Now, my colleagues, what's important here, my home audience, is that you know how to take the magnitude and the phase of a high-pass filter. Now, we've done low pass a few times. Let's make sure you're okay with high pass, okay? So, first thing I do is I write V in. In vector form, That's 100 at an angle of 30. I then say, okay, let me plug in to the answer from part A, R1, R2 equal 10, L is 1 millihenry. And by the way, I hope you can see this. Help me out. I don't want you to lose points on this. The input frequency is 100 hertz. Do you see that? Because it's cosine 2 pi ft. Let me just make sure you got that right. It's written as cosine 2 pi ft plus theta. That's like some value a. So notice what I give you is 200 pi t. 200 pi t equals 2 pi ft. So you should be able to get that the frequency is 100. Now go back to part A and put in the values for R and L. And I get this value for h of f. Just plugging in the numbers now. The numbers for R and L, R1, R2, I think it is, and L. And I get this. Now, here is the part I want to make sure you're solid on. I now have to get the magnitude of this. That means if we're dealing with vectors, that's the length of the vector. So I want the length of the vector. So I need to get the magnitude of the numerator, the magnitude of the denominator. This is a vector who points in the j direction, whose length is 6.283. Done and dusted. Okay? That's the magnitude. How do I get the magnitude of the bottom? We've done this a lot with low pass. It's the Pythagorean theorem. Now be careful with the angle. My colleague, I'm thinking of you, your great question before. The low-pass filter had a 1 in the numerator. So what was the angle? 0 degrees. Here, we have a j something in the numerator. So the angle is 90 degrees. Minus the arctan of the denominator, and I get this angle here. Now, h of f is v out over v in. So what we get is h of f is v out over v in. So v out is v in times h of f. Now, what is f? F is the frequency of the input signal. I see people still copying, so give it a moment. All right. So now, continued from the previous page, V out is V in times the transfer function. And there we have it. I ask you in the problem statement to write it in cosine form, so hopefully that's simple. Their frequency does not change in these filters. So I get 6.23 times the cosine of all of this. And I think we're in good shape. Good. How are we doing on the high pass, getting the magnitude and the phase? That's the key. All right. I see people still copying. Now, in this part of the problem, I said R2 goes to infinity. All right? So in this part of the problem, I said R1 is 25 ohms, but R2 goes to infinity. R2 going to infinity, that's now an open circuit. What, they don't think we have classes after 11 o'clock at night? It's an open circuit. I hope I can get it back. Can I get it back? see that it takes a while for the projector to kind of cycle through. Wish I had some funny stories or something. I have nothing. I have nothing. Huh? My weekend was good. I didn't do anything, though. I came to work feeling guilty. Everybody get that? Yeah, you feel you should be working, you're just exhausted, and then you wake up the next day and you're guilty. Feeling guilty. Not that you're guilty of anything. I'm just feeling guilty. The projector is not coming on. Ah, here it comes. I might need Kappa Sig again. Wait, let me see if I can do it myself. This now, like, I'm just wondering if I can possibly do it. Just the mere fact that you looked at it, that sent enough fear into it that the projector worked. All right, thanks everybody. All right, so what I do here in this problem is I let R2 go to infinity, which makes it an open circuit. Now I'm wondering, is this something more familiar? This was the high-pass filter we looked at in class. So I say, I ask you here to do a few things. Determine the transfer function, the break frequency, and determine the numerical value of the break frequency. By the way, this is making me nervous. It's time to replace your lamp is what it was saying here. Marcy, I don't know. I don't want to know that danger here. All right. So here, using voltage division, I take the reactance of the inductor over the resistor plus the reactance of the inductor. And as my colleague and I were discussing, standard form is a 1 plus something in the denominator. So I got to divide everything by R1. So I get L over R, L over R1. That's the time constant for an RL circuit, which is also related to the break frequency. This ties it all together. So we're going to define the break frequency as 1 over 2 pi tau, which is 1 over 2 pi L over R1. And I can then write this as this, okay, which is the answer, 3 points. And then I say, okay, what's the break frequency? Easy, just plug in the values. It's 1 over 2 pi tau or 1 over 2 pi L over R1. You get a break frequency of around 39, almost 4,000 hertz. All right. Whoops. I heard scroll up. You know what, Marcy? I'm wondering if I could ask a favor at the end of this review. Just so my family knows where I am. Could we take like a selfie? Whoever wants to be in it, I think that'd be a goof. I don't know what we can do, but we'll see if we can get a camera just to take, and you don't have to be in it. There's no extra credit if you're in it. You don't lose any points if you're not in it. So let's just see if we can get the camera, just so my family knows what I do, you know? I just say I'm doing a review. Oh. Oh, and listen, I tell my family I'm on YouTube, and I told you this. My son says, how many likes do I get? I'm still kind of low. So look, if you like this, give the old guy a thumbs up on the YouTube. That's all. I'm not asking much. I'm not asking much, you know? And then, you know, I'll show my son, hey, come here. You know, I'm liked. You know, it might help me out a bit. But that's all. You don't have to. You don't have to. But it might be nice. All right. All right. So now, the Bodie plot. Da, da, da. Now, I wanted to make sure you knew everything, so I had you fill in the blanks. Because you could argue, well, I didn't know we had to add that to the Bodie plot. So I asked you to label the axes. What's the slope? What's the value at 0.1 f sub b? So I say, look, we have a high-pass filter. That you got to know. Okay? So we say, I know how to draw a Bodie plot for a high-pass filter. Right? Now, notice, what did I not do? See, I must have gone easy on the 2014. What didn't I do? The correction factor. What was I thinking? I probably wasn't thinking. This is my problem. You got to put a dot right here, right? And that's minus 3 dB. And Marcy knows this. We then connect it here, and we're all set. All right, so the label for the x-axis, for the y-axis, is magnitude of h sub f in dB. The slope of the low-frequency asymptote, that's this line here. It's positive 20 dB per decade. The slope of the high-frequency one is 0, and the value of the Bode plot at 1 decade below the break is minus 20, because it's 20 dB per decade. How do we do? We got one last problem, and you have survived. You have survived the review session. A question. I heard a question. Oh, the slope we just know is 20 dB. Yeah, for first order. And notice for the question is it always 20 dB? Two thoughts come to mind. This is 20 dB per decade. A low-pass filter, minus 20 dB, because it starts out flat and then breaks. Can I ask you a question? Can I put you on the spot? What would be a third-order filter slope? Third-order high-pass. Very good, 60 dB. 20 dB per decade for each order. Fantastic. Way to go. All right? So first order is 20, second 40, and so on and so on. Third order 60. You got it. Last problem. Da, da, da. Okay. All right. All right. In this problem, the analog to digital converter has a sampling rate of 44,100. What is the highest allowable frequency into the A to D converter? Remember the number 2. The sampling frequency absolutely has to be at least twice the highest frequency. So if you tell me the sampling is at 44,100, the absolute highest frequency is 22,050 hertz. Next, 80-minute period of music. How many bits? Easy. Follow the units. You can't make a mistake if you write out the units. This many samples per second, I tell you here somewhere, there's 16 bits. Where do I tell you this? Yes, the top line there, my colleagues. Top line of the problem statement, 16 bits. Each sample is 16 bits. So you have 16 bits per sample. For 80 minutes, 60 seconds over 1 minute, we get a huge number of bits. All right. Now, I think the very last part is the very last lecture we had. So you might want to make sure you can practice this and you're comfortable with it. This is solving a difference equation. Okay? All right, so I give you an equation. Let me kind of walk you through this so both of us feel that you're going to do it great. I want you to have confidence when you get to this. Okay. So the equation is, and Marcy, make sure the blue is good for you still. Good. All right. Y of n equals, it's Darcy, isn't it? Am I saying Marcy? What am? Oh no, it's no excuse. I should know. Darcy, please forgive me. I'm sorry. I just realized that it's not, you know, this is what happens. You work after 10:30, 11 o'clock at night, all bets are off, you know. Darcy, I'm so sorry. You're here working hard for us and I'm getting your name mixed up. a times yn minus 1 plus 1 minus a times x of n. Okay? Parameter a is a constant, so a is allowed to be in your answer. Now notice x of n is 0 except when n equals 0. That's different than we had in class. Okay, so I changed the input. So x of n is 0 for n less than 0, for n greater than 0, except at n equals 0, x of 0 equals 1. So I say, all right, what's the initial condition? Y of n for n less than 0 is 0. Okay? So I say, all right, can we now solve this? My colleagues, just take a deep breath and go through it step by step. I write it out. Let n equal 0. So we have n equals 0. So I go to this here. Let me do this with you. N equals 0. So y of 0 equals a times y of 0 minus 1. This becomes minus 1. Plus 1 minus a times x of 0. Okay, just plugging in n equals 0. Now, y of minus 1. Wait a minute. Y parenthesis n is 0 for any value of n less than 0. So this equals 0. So this becomes y of 0 equals 1 minus a times x evaluated at 0, which is 1. So what we get is y sub 0 is 1 minus a. Do it again. N equal 1. Y of 1, again using that equation, is a times y of 0. I tell you what, I want to make sure you get this. Okay, so now n is 1. Y of 1 is a times y. 1 minus 1, 0. Plus 1 minus a times x of 1. Every value of x except x evaluated at 0 is 0. So this is 0. And I say, what is y of 0? Help me out. That was 1 minus a, right? So it's 1 minus a. So what does y of 1 become? A times 1 minus a. My colleagues, keep going until you see a pattern. If you do y equal 2, y of n equal 2, y of n equal to 3, you'll see that it goes a times 1 minus a squared times 1 minus a, and so on, a cubed times 1 minus a. So how do you write it in general? Thomas, help me out. Wow, if you see the pattern at n equal 1, you're great. Just be careful. Make sure you're right. There's no appeal here. I mean, there's an appeal if it's marked wrong. But look, again, you got 4 hours. Make sure, convince yourself you really do see the pattern. But you're right, Thomas. There's no magic number. Keep going until you see the pattern. So in general, y of n is a to the n 1 minus a. How do we do? Extra credit. Just for fun, these topics came up in class. I don't know how. Please only answer the question for your section. All right. If both questions are answered, wrong. Okay? So it's 3 points. So they asked me what was my first car. All right, so my dad gave me his car, 1972 Oldsmobile Cutlass. All right. And then what was one specific thing that Bodie did in World War II? He was actually on our side. And he came up with anti-aircraft gun guided by radar, which in World War II was pretty cool. So we actually had discussed both of these in class. So that was just for fun. All right. Good? Do you want extra credit? All right, just for fun. All right, extra credit. No points deducted, but you got to be right to get the full. There's no partials. All right? So I'm not going to tell you what the questions are. They're not related to any, well, I can't say they're not related to the course. You will know this. You will know this. If you've been coming to class, you will know. I think they're fun. I thought of it the other night going home in the car. This is the problem when you have an hour drive and you don't know what to think of. So I have some fun extra credit questions. I think there'll be 3 of them, one point each. So you get 3 points, and if you don't get it, you can't lose. Okay, you can't have points deducted, just for fun. I think that's it.